or something like that and see the rate at which it disappears with the rate at which your iPhone camera descended down to the ground, and you could calculate it out. So anyway, I encourage everybody to go out and do this. I've seen videos where people have tried to debunk this, but in almost every single one, you see the flaws in how they set this thing up. They're not close enough, and B, they're not even getting down to the ground. You know, it's just it's not a full 100% effort to do this. It's a little bit deceptive, in my opinion, because this effect is almost its diffraction is everywhere. You cannot get around it. I'll put it that way. So I just kind of model out how perspective works when you have objects now within your perspective and they move away from you. And the only thing I just want to really quickly talk about with this is that wherever they are, you model them according to orthogonal lines as they descend away from you. And so what that means is that if this object is here starting out and it goes towards my center line, it will never cross over this midpoint ever, right? And suddenly jump to the other side as it descends or gets further away from me. So if I model this for something on the bottom of me, if my eye line is above the top of this object, okay, it will never suddenly at some point in the distance get higher and then lower. It always stays below my eye line. And when it disappears, it will disappear as a point. Okay? Okay. So I just kind of model out some other things. Now you have an object down on your lower left and it kind of descends away from you. It's always going to stay between these two orthogonal lines as it goes away, right? And all the lines within this box must line up to those orthogonal lines, okay? So this box, like when you model out a box, you typically make these two lines parallel, right? When you do a box in 3D, you typically put a line here, you have a box, and then you go, okay, depth is here and depth is here. You can't do that within perspective. You have to model this line, this top of the box. This has to be going in this along this orthogonal line. And this part of this box, or this part of the box, must be going along an orthogonal line that you can't see right here, but it would be going right through here. Okay? And the bottom of the box, this line is lining up perfectly along these orthogonal lines, or this line. Does that make sense?
Absolutely.
Okay. So here's what I'm showing, kind of what happens again within perspective. As I lower my eye height, these lines down here, these potential visual field angles with which I'm viewing the world, they get compressed, and the upper ones expand, and my eye line within this reference frame, within this green box, gets lower down along the box. Okay? All right. And all these things become important later on. So I just want to kind of lay this out. And again, I'm just modeling this like, okay, now we're going to look at something that's a little bit above my eye line and a little bit, and most of it below, right? As it starts out. And now it's going to move away along the, I just modeled out some black orthogonal lines here. And it's going to move, these corners are always going to line up to those lines as it moves away from me. And what you'll notice is that the same proportion of this above and below is always the same proportion, okay? It doesn't like hop above and below this purple line, okay? So what that means is that everything below is compressing at a higher rate than everything above, okay? Because you have more of it below to start out with, right? And as it moves away, you're taking more of it and compressing it within the same space, okay? Does that make sense? You guys are pretty...
Yeah, I mean, no, I mean, it... if anybody's been following the debates and stuff and the work that's been going on this year, they know this. They've seen it with real world photography. So to have it modeled out just like this, it's kind of just putting the final nail in the coffin, really.
So I took these ones, and now I'm trying to show this where you can't, it's moving away from you, but you can't really see what's happening to the bottoms of this in this view. So I made them a little transparent. And so now you're seeing through the boxes, I guess, as they're moving away from you. And now I just modeled it like it starts out above your eye line and now it's below. And again, each corner lines up to an orthogonal line. But look what happens to the blue lines, okay? So I had to zoom in on this to blow it up. But you can see how the blue lines are getting indistinct. You can't make them out anymore. But the top lines, I can see the boxes still clearly all the way down to this level. Here, it's all become one smudge, all like one line,
Yeah,
right?
don't move off this image. You see where that smudging starts and everything seems to become indistinguishable. It all becomes like one color, this blue. It's got rid of the orange essentially. Well, that is in the area where I'm capturing this inferior mirage.
Right, that's exactly right. So I'll go over the inferior mirage a little bit later if we can get, if we hope we can get to it. But that you're looking at shallow angles. That's what I've come to with the inferior mirage. Those are very shallow angles of a distant floor, if you will. It could be a distant road. It could be, it's in this case, it's the water line with emission refraction creating a low density layer. And you're getting essentially what's a critical angle met, and I'll go through that later, and where your refraction angle becomes a reflected angle, and the reflected rays from the bottom are getting shoved away from you. You don't ever see them, but instead what you're seeing is the reflected rays from a more dense layer above hitting this less dense medium and reflecting to your eye. So we'll go through that a little bit later. But you're exactly right. I mean, that's kind of what's happening is the angles are getting so shallow that they meet a critical angle. And that has more to do with refraction in that sense than diffraction. Okay. But it's the same concept. So modeling out some, if you can start putting little like objects within your perspective, right? So we'll put, this is orthographic of these three mountains. Okay. And they're right behind one another. All right. And they're all the same size. So how would that look in perspective? Okay, they would descend in size by a rate of, half the distance, double the size, or h1 or h1 over h2 equals d2 over d1, or the height is inversely proportional to the distance. Okay, so half the size, double the distance. That's the bottom line, right? So I kind of half the size for each of these, considering that I was doubling the distance here. Does that make sense?
Yep.
All right, so you can do the same thing with a car, but in the car example, I didn't really compress the floor to the degree you would kind of need to, but I just try to model that out. The same effect would kind of occur if I got really down to the street level and put my eye line right where the bottom of the tire was. I would see this car do the same kind of phenomenon. So it's just how perspective works, and so now I just threw in. Now I got some mountains at different positions along my orthographic view, essentially, but they're still kind of getting smaller with distance. Here's my same three mountains again, and now I throw in some clouds. The clouds move along these potential orthogonal lines, and now you have a panorama, right? This is just how our vision works. So then I just kind of summarize everything by essentially just a linear equation, right? If I get higher, I see further, and if I get lower, I see less far. And that relationship is here. Does that make sense?
It does.
And so,
sorry, I'm just making a comment now. I've put 0 likes and 14 dislikes. I mean, I don't know whether it's YouTube messing around with the likes and the dislikes right now, but that's kind of some crazy stuff if that's true.
So I plugged this. I plugged this live stream on like my community post here on YouTube. I plugged it on Facebook, so who knows what the hell is going on? I don't know. Maybe YouTube recognizes I'm in here, so they're fucking with it. I don't know.
Well, it doesn't bother me. It's again, I want the truth, So none of that stuff bothers me. It's just to me, this is the truth. This is how we see the world, and it's been overlooked. And you can argue whether it was purposeful or not, but here we are, right? So I just want to get down to what's happening. And so I think this is the truth. This is what's been happening. Obstruction is not physical obstruction that they're touting it as. It's optical. It's an optical obstruction. And this is how optical obstructions occur. And you can scale it for yourself by doing. That's the thing, right? Everything should be scalable. All these effects, gravity, whatever you want to get in, whatever your topic, you should be able to scale it. And the fact that we have so many theories out there about how everything works that are completely not scalable, it bothers me. So because they're not, it's you get into that whole, is it pseudoscience or not? So anyway, all All right. So that's basically part 2. So in part 3, then real quickly, I just kind of get into where this formula came from. Okay. So this is the formula for angular resolution limit. And there were a couple different formulas for this. Abby put one forth, Rayleigh put one out, and they were around the same times. But Abby's has kind of been more, and all of them have to do with how far away an Airy pattern essentially can be from one another in order for it to be resolved. But the more common one to be using kind of out without a microscope, I guess, without different refractive media that you're looking through, is Rayleigh's criteria. And so that formula is theta in radians, so you have to convert radians to degrees, is equal to 1.22 times the wavelength divided by the diameter of the aperture. And I kind of go through where the 1.22 came from. I was like, man, where's that 1 to it? And it's a lot of math, but it's something called a first order Bessel function. And all it really means is that if you take let's say a rope and you tie it to a wall and you kind of give it an amplitude of energy, that energy kind of fizzles out, right? If it was a long rope, let's say, or let's say you drop a pebble in the water and it creates a diffraction pattern. Those ripples kind of get less energetic as they move away from you, right? And they kind of widen out and flatten out. Does that make sense?
It does. Listen, Travis, Nathan Oakley's just joined.
Oh, hey, Nathan, how's it going?
Hello, good to be here.
Yeah, thanks for man, your flashlight on the floor thing. That kind of pushed me over the edge. I had to do it a few times and prove it to myself in several different buildings, and it's like clockwork. So kudos for pushing that out.
Ooh.
But anyway,
don't interrupt. Thank you for the compliments, but yeah, I'm really here to hear you.
Yeah, sure.
Nathan's your biggest. Well, he's your biggest fan now. I mean, I was originally your biggest fan. I think he's taken over that now because, as much as you're on my channel right now, but he's like loving the fact that we've got this angle, and he's absolutely loving it. So, just thought I'd say that.
Yeah, no, sure. I like I said, I just want the truth out there. I'm not like a person who's like going to be I think a content creator or whatever. I just want to. I kind of want to get us all on the same page. And let's say I'm wrong on some of this stuff. I want to start the conversation at least so we can get on the same wavelength. You know what I mean? And just kind of starting to put numbers and different observable phenomenon to our I guess theory or whatever you want to call it about what's going on.
Oh, and sorry, Nathan, Chris is here as well. Red Pill.
Hey, Chris.
Yeah, what's up, Nathan?
So, so continuing on, so the essentially it's like a damping effect, right? Is what you're observing with this 1.22, and the 1.22 really just has to do with this central maximum. This red line, I guess if you want to call it right here, this diameter is this diameter down here in this scenario, and you're interested in this function here. So this is the first order Bessel function that you're interested in, and they have different numbers as you go out in radius. So that's all that number really means. I used to think it had other significance, but that's essentially it. And so what you're concerned with in this pattern, this is a diffraction pattern of water, this is a diffraction pattern of light. You're interested in this central maximum here, this bright fringe in the middle. And so this is just that kind of image blown up a little bit, and you can watch MIT lectures and everything about how you kind of can model this out. But this is the diffraction of light, right? This is the pattern that's being created on the back of a screen, let's say, when light is diffracted. And all this means is that when you decrease the aperture, it diffracts more, okay? And it kind of like scatters out more and creates a larger disk. So that's what I'm trying to model here is the radius of this disk is bigger the smaller the aperture. Does that make sense?
It does. Okay. One thing I thought you was going to just touch on then, you might actually be touching on in a minute, is I did a presentation on Globebusters probably about 5 or 6 months ago now, where I actually reverse engineered the curve calcs. And I know we were talking a bit off air before we went live, and you said a similar thing. It was It was like, oh, you actually saw that presentation on Globebusters?
Yeah, I did.
Right. Wow. What did you think?
Oh, it was great, man. Yeah.
Yeah, because I mean, literally, you compressed the top image from 30 foot, compared it to the 1 foot observation, and it was essentially the same. It was identical. Right. And you were touching on this because you said that you've got some kind of calculator that you've worked out.
Yeah, well, we talked about it a little bit earlier that people seem to need a calculator to verify these effects for them. I don't need a calculator. I just need a scalable phenomenon that seems to work and show me that things are optically cut off, right? I do want that, and I have that, and then I need to know, number two, that light can bend and refract and move all over the place, and you can see that in the Skunk Bay time lapse. That's just one video, and you're like, okay, I can essentially make very little conclusions from any observation over the sea as proof of something, right? Without taking into consideration all those refractive effects that occur.
Yeah, but one thing I have found though with my observations is that I've yet to find looming. You know, I've literally gone out of my way to try and find it. I have a post that's actually nailed into the floor, basically 4 miles away from me. I can film from the same location, film the same buildings. They never change in relation to each other in height.
That's John Dee's point, right? Is he's logged all these hundreds of hours over water observations, and he says basically the by far predominant. I'm getting a little bit echo there, but by far the predominant thing is upward refraction, is emission refraction phenomenon, not absorption refraction and downward refraction, which is what causes looming. Yeah. So if anything, the horizons are always higher in real life, and they're brought artificially lower. That's what's happening.
Yeah. Well, what I meant to say, going further from that actual point, was that I get a lot of distortion in the right. Let's say I'm looking at a building that's 200 feet away at 18 miles, 200 feet high at 18 miles away. I get a lot of distortion at times in the lower 100 feet or so. From an elevation of approximately 30 feet, I will get a lot of distortion at around about 100 feet in height. But the top part of the buildings always stays level with the post in the foreground. It never changes, but the bottom it has inferior mirages, it has blockage, it has all kinds of different things going on with it. But there's never looming. There's never looming.
It's pulled and stretched, and like I said, you just watch a Skunk Bay time lapse, which is like, I guess, the most famous one. But or the Chicago skyline time lapses, and you'll see all the floors compress and expand, and sometimes mirror and then go back to normal, and these are time lapses over like 12 hours, right? And so you got to think to yourself, okay, I'm taking a snapshot in time of one of these effects, and how can you draw a conclusion from that necessarily, right? There's so much refraction going on that it's like, I just don't understand, how that's conclusive of anything. So anyway, but that's refraction. This what I'm trying to lay the groundwork here is for how do you get to resolution from the formula, okay? And so this was our formula, right? And this is kind of what we're describing, is the fact that the smaller the aperture, this is the wavelength of light going through here, and then some variable distance L is creating an angle from a straight line that gets larger with the smaller the aperture. That's all this is saying. I increase my aperture, this angle is smaller, okay? And this angle is going to represent the radius of this central maximum of this airy pattern, okay? This is the airy disk. Does that make sense so far?
Yeah, absolutely.
At the smallest of aperture, you're going to get an increased pattern
radius
at the other end. So, just to qualify this, so I understand, or think I understand, I'm just qualifying it with you, I might be wrong. So in terms of when we see things like the light splitting in two when someone lowers a light into the limited angle, the actual light splitting apart, is that what you're describing in terms of it being a larger pattern at the end. Are you describing this at the limit is what I'm kind of asking.
No, all I'm saying is that for now, that as light goes through an aperture, it's going to scatter to a certain degree based on the size of the aperture. The radius to the central maximum is going to be theta, for that particular aperture and that particular wavelength is going to be theta, which is this theta right here in radians. That's all I'm saying here. It's more conceptual, I guess. Than anything.
Okay, so I'm taking 2 steps forward. So this is just at a very base level. Any light coming through a smaller aperture will give a bigger diameter at the end.
Yeah, that's exactly right. That's all I want to say right here. Yep.
Fine. Okay, I'm jumping ahead. I'm sorry.
And there's all kinds of, like, you know, Young's double slits experiments and Huygens principle and everything you can get into. And they're very cool physics lectures online that go through all that, and double slits versus single slits. And you come to the conclusion that these patterns are essentially as if it were a single slit. And I'm not going to go through all that, but they're kind of cool. Light is very cool, I guess, in how it acts. But that's what that is. You just get a larger diameter with a smaller aperture. And so what they found was that now let's say you're doing this twice, okay? And you're getting 2 different airy patterns on the back of whatever you're looking at. And you're now going to get these patterns to get closer and closer to one another, okay? So that's now where the resolution aspect comes in. So you can see here we got 2 patterns. Here we got 2 patterns. Here, not so much, right? It's one pattern. I can't say within that 50%, within this, whatever distance this is, I can't say that that's 2 patterns overlapping. Okay. I've now taken 2 images and they're now 1 to me. I've lost 1 image.
Can I just qualify what you mean by that? So if I put that into photography terms, so the top one where it says resolved with 2 dots, that would be like 2 pixels represented in your camera. And let's pretend for a second that a set of car headlights is 4 pixels in total. So the top one is a set of car headlights at 5 miles, whereas if you get further away from it, they're going to get closer together. And as you get further away from it, still those headlights merge into one, and that would be the point that you've no longer got the resolution to resolve it.
Right. Another way to look at it is you've lost an image. You've lost 1 object.
Right. Okay.
At that point. So you can model this out with some circles. Now I qualify this by your circles. These I'm showing that these are actually of equal amplitude because I didn't fade them out. Right. So it's not really a Bessel function in this case, but you can see the point. All I'm drawing here is that there are overlap points, interference points that you can draw out. But that was kind of like one of my other theories about what may be going on. It's not really relevant to the point at this point. But all I want you to focus on is the radius of the central circle, which is right here in the middle. Okay, and that's with the brown line. And I'm just going to slowly kind of push these 2 patterns together. So if we do that, we go from this to this to this to this to this, and you see how we're kind of, it's very hard at this point. We're not at 50% overlap yet, okay? But you can also see how this has become essentially like 1 image, right? All these circular, all these different circles have come together to become kind of like a merged. And you can see here in when I put these 2 area patterns together, you can still see that there's 2 distinct points in the middle, but it's getting very hard to see. Does that make sense?
Perfect sense, yeah.
And then now we get to 50% overlap, and this is what you see. This is the point where your brain says, nope, I've lost an image here. There's only 1 image there, and that's what Rayleigh essentially quantified. Does that make sense?
Right.
Okay. So now the question is how does the thing vanish, right? Why is it that we can't see a human hair on the ground, and it's not just a smudge of one thing? It's just nothingness. And so as you can, when you get these 2 focal, or these, let's say it's the 2 rays coming off the bottom of the tree and the 2 rays coming off the top of the tree. The top of the tree is a little bit taller than the bottom of the tree. in this scenario, which means that the bottom of the tree is smaller, okay, than the top of the tree. And so this distance here, as it travels, these two light rays are closer together than when you're looking at a larger object and they're further apart, okay? And so, or taller versus shorter, you just look at it that way. So there's less overlap between the taller, let's say, version of the tree versus the shorter aspect of the tree. And what happens with these airy patterns within these two light rays, as they get closer together, they start to merge into one, okay? And what I would argue is that when this point here occurs is when your brain says, I don't have contextual information to create an image from this point. I don't have a second ray with which to create an image, and an image is not formed. And so I've gone through several papers, and image formation it's very hard to find information on that, but that appears to be what's happening, and that is again these micro saccade experiments with retinal stabilization, where things just they vanish when you cannot scan and move your eye back and forth. Things disappear. It's because your brain or your imaging system needs context with which to form an image. That's the simplest way I can put it. The reason it happens in a camera the same way would just be it's the same phenomenon, but it's like a wavelength of light issue, or it could just be the pixel issue, but the same effect occurs. Where there is no contextual, there's not a second pixel, there's nothing else with which to create context.
Yeah, I use a person going into the distance, or a wall, or anything. So you got a 6-foot man, and you get to a mile, and he might represent 5 or 6 pixels in the camera. You go to 2 miles, he represents 2 pixels in the camera. You go to 10 miles, and he's no pixels. In other words, from left to right in this depiction, it gets the 6-foot man's merging into nothing and then disappearing.
Right. His angular size is such that it fits within 1 pixel. Right. It's less than the diameter of the 1 pixel, you could say, and it's registered as like a point of light, which is nothing. It's just not registered as an image. So, yeah. So then I go through some practical examples about how you can kind of calculate this for whether or not you would see a bug on the floor, or whether or not you would see a human hair on the floor. And I won't go through that here, but all you got to use is a little bit of trigonometry. And you model your image height here. Because this image is so far away, you can use it as a right triangle, because both these angles are essentially very close to 90 degrees with a small angle.
So yeah. Travis, Nathan uses quite often, he uses the ankles going first, and then the knees, and then obviously the rest of the body. Is this what you'd say would happen if somebody just carried on walking away in a perfectly flat surface, just kept walking away, and walking away? They would slowly start to disappear from the bottom up.
Right. So that's what I kind of argue is the combination of perspective and angular resolution. So the two arguments are that small things get smaller with distance, part 1. Number 2, small things disappear, right? Number 3 is small things disappear with distance. And so that's the basic argument. So yes, in a nutshell, that's why the things disappear bottom first, because you've compressed the lower 50% of your vision is now getting compressed into a smaller space. That's the best way I can explain that part without showing more diagrams.
I can get, there's a Flat Earth Perth did a video, and he's got a piece of grass, and all he does is raise and lower, and he shows that as you're looking across it from a lower elevation, you can see less of it. You've got a more limited angle to the grass, therefore you see a thin sliver of grass. However, if you've got a post, which he's also got, coincidentally, just doesn't detail it, he's got a lamp post, which looks pretty much the same from both heights, because you've got a wider angle to it. But the grass, the blades of grass, it doesn't matter that there's lots of them going into the distance. When you lower your angle, you've got less grass that you can see. Well, the same applies to all the bugs in the grass. You're going to get a lesser angle to that lower piece, i.e. the things at the bottom. So they're going to reach the angular resolution limit quicker than the things that have a higher elevation from your position, like the lamppost. So yeah, the stuff is always going to disappear bottom first due to a combination of perspective and angular resolution. You summed it up beautifully. Life is short. Couldn't have been better said.
Yeah, you're essentially compressing. You've compressed your visual, the potential with which you view the world, right? When you get lower down to the ground, you're compressing all those lower visual field lines, and so they reach theta, right? This angle here sooner than they did before, and so you're bringing your lower horizon inward, and so you don't see as far along the floor, and then the things that were beyond, right, between, let's say, distance 1 and distance 2, are now gone. So I don't know. It's simple to me now, but it was a little bit of a mind bender to come to terms with it initially.
Nathan, look at it this way. Something was said earlier on about paintings being on the ceiling. And I kind of want to adapt that into a different way of trying to understand this. Is that if you are lying on your stomach in a room, right, and you have all the walls painted in newspaper, so it's got newspaper all stuck to the walls, the ceiling, and the floor, right, and you're on your belly on the floor, right, how far would you be able to read the newspaper on the floor?
Yeah, not very, because of your limited angle.
Yeah, and then at some point, all the words would all just merge into the same, and you wouldn't be able to distinguish them. But looking up at the ceiling, you'd still be able to read all the newspaper, the same on the walls. But on the floor, there would come a point where you wouldn't be able to see it.
Yeah,
absolutely.
So here, I don't know, what am I doing here? I just kind of go through a range of diameters of pupils that you can use and the range of wavelengths that you can use to come to different theta values. In general, though, we see at 1 arc minute. Okay, most vision is between 1 arc minute and 0.03 degrees. 0.02 to 0.03 degrees is where most human vision is. And most cameras seem to be around 1 arc minute. Now, if you go up to telescopes and all that stuff, they get much less, which means you can resolve more at further distances, you know, as 2 distinct objects. But that's all that. I'm just kind of throwing numbers out if you want to mess with this on your own. But what I did was I just took 1 arc minute as our average, and that's kind of what I used throughout the rest of it. Is 1 arc minute is going to be our number. So when you calculate all this out for what you can see at what distance, we would lose 4 feet at 2 miles, 6 feet at 3 miles, 8 feet at 4 miles, 10 feet at 5 miles, and you can just keep going. But what do you notice about that? It's linear, right? It's a linear loss rate. It's not exponential. It doesn't just jump at some point to like, okay, now we're losing, 6,000 feet at 20 miles or whatever the number is, right?
What you're saying is it's not a squared function. And as Ranty points out with the wind turbines, these things aren't curving. They're following a linear pattern.
Yeah, exactly. And so then I kind of put this to the
unless it's Soundly's Pontchartrain, and then it's curving, right?
Well, and I kind of, you know, that's another one. We can get to that later. Kind of what's going on there. But it's just another upward. It's just upward refraction. And when they was doing this live stream, someone put I was asking for what's the water temperature, what's the air temperature, and I was telling them if you shone a laser light from the opposite end, it would bend upward to the observer. And someone posted the data, and the air temperature, water temperature difference was huge. The water was much warmer than the air where he was. So again, it's emission refraction. So. But anyway, going to the, so I just kind of plug in this arc minute now as my angle with which I'm standardizing H1 over H2 equal to D2 over D1. And you can now see that if I gain myself height according to this angle, keeping similar triangles, I gain a distance of this much. And
sorry to stop you.
Yeah.
You can say all of that again really slowly. I didn't get any of that.
I'm sorry. So,
what's does H1? Is H1 height and D is
H1 is height and D is distance. H is in feet and D is in miles.
Okay.
So if I'm at height 1, which is my green guy here, and I move up to height 2, okay, I now see from distance 1 to distance 2. I see further.
Yes. Okay.
According to this angle. Okay. So if I go lower, if I go from H2 down to H1, I see less far. My horizon has been brought inward, assuming I'm seeing with the same arc minute of angular resolution. That's what this formula is saying.
Okay. I understand that. Do you understand that, Nate?
Yeah, it's actually very simple.
Yeah. And
yet so hijacked. But anyway, we'll get into that later, I'm sure.
Yeah. This is for just diffraction. So I can do this for any number of distances to solve for height or distance using this theta. And so for height, again, we already mentioned I lose 4 feet at 2 miles, 6 feet at 3 miles. The corollary to that is for distance, I see 2 miles at 4 foot elevation. I see 3 miles at a 6 foot elevation. I see 4 at 8 and so on. Okay. And again, you might have to like kind of digest it a little bit for that to make sense, but it's just this formula. Double the distance, half the size, according to at this rate, or at this angular resolution. So
it's complicated in mathematical terms, but in terms of physical terms, it's not at all complicated. Go and lie on the ground and then stand up slowly. You will observe exactly what he has just described.
Right. So like for this formula, let's say the whole double the distance, half the size thing. Let's say I took my green guy here, and this lighter green guy is now standing on top of the darker green guy. So he's doubled his distance. Now this guy, let's say he's 6 feet. This guy's 12 feet high now. This line right here would be twice the distance of the first line. That's what this argument is saying.
Yeah.
Okay. All right. So then I kind of start getting into how this is affected within perspective. I'm not going to go through all these examples because it's a bit of a mind bender. I just encourage you to kind of work through them on your own. The bottom line was that if my eye line is at the top of a cruise ship, let's say, and I'm watching this cruise ship go away from me, it's going to move away from me until a single point, according to the compression rate of my lower visual field. So if it's a highly compressed visual field, this thing moves off into my vanishing point quicker. If it's a very less compressed visual field, it moves away slower. So the higher I am, the longer it's going to take for this thing to compress down into a point. And so I'm also showing now, what if I had a cruise ship that I'm in the middle of with my eye line? Now I'm like the middle 3 decks, or the lower 3 decks and the top 3 decks. Well, this thing is going to move away at the same angular rate, but at a certain point, the bottom is going to vanish. Okay. And the top is still going to remain. Think of it as the bottles or whatever. I show a better diagram of this down the road, but that's how this curve, or this optical obstruction was taken as curve, was because you're just losing the more compressed aspects as they move off into the distance.
I like the term the lower visual field. I like that.
Right.
Before you move on, I just want to clarify something, because it was in the video I watched that you did. So yes, the lower visual field. I don't want to distract from that. Yes, it's more compressed. Absolutely brilliant. But you're describing the eye line. Now, what is the eye line that most people would observe, say, looking out over water? What is that line?
Well, so it's just the point where the ceiling meets the floor. Right?
It's the horizon.
It's the horizon.
Okay. Just wanted to make that clear for the audience specifically. So that line drawn through his eyes is the horizon.
Yeah, it's the horizontal orthogonal line, essentially, the horizontal vanishing line. In this case, because I've compressed it against a floor, and so it became a line. And I modeled this here. Honestly, I may have overlooked this, but I did model this with walls. So like how we did in part 2, where I had all these, these had walls, right? And let's say these ones didn't, right? There's no walls here. This is more what it would be akin to, where there's no walls.
The reason I want to labor the point is because you're describing your visual acuity. Is that what you called it?
Well, visual acuity is like a I guess a tangent off of angular resolution, but yeah, they're essentially the same.
Okay, but the reason I'm laboring it is because you've got this line, this nice line drawn through his eyes, and then you've got the point that the ground meets the ceiling, and these are all effects based on resolution and angular size and angular relationships with your bottom visual field causing things to compress. But that line is, if you're a globe head, the leading edge of a sphere. All of these are ignored. None of this is considered. But that line that you're drawing and describing is actually what they consider to be and mathematically calculate to be the leading edge of a ball.
Right. So I brought that up with Ranty before you came on, was that they say that they factored in perspective to an earth curve calculator, but perspective means that the floor meets the ceiling. And so full stop at that point, that it's not curve, it's just perspective. They're not the same thing. So
okay, I came in late, my bad. Worth laboring anyway, just to rub it in.
No, it's the point, I think, really, or at this whole thing. So, all right. So here's a practical example, I guess, of H1 over H2 equals D2 over D1. Again, I am assuming no refraction here. There probably was a small amount of refraction, but let's assume there's not. It's a clear image. So I guess it's Daza, cameraman. He has a cruise ship, and here's this more close up within the video, and he's showing this cruise ship go off into the distance and vanish over the curve, right? And he says he's at a 6-foot elevation. I'm showing the arrow where the cruise ship is, and then he goes up to a 30-foot elevation, and he zooms back in on the ship. Well, he brings back 30 feet of the ship, right? You can see it's roughly 3 decks worth, comparing it to the. Again, it's a linear relationship between height to what is being resolved. Again, this assumes very little refraction, but that's what that relationship means. Okay.
So can I just I want to ask the chat something right now. It's totally off topic, but it's just that I've had an email from this airline pilot research. This guy, this Wolfie gentleman, and he's basically sent me a link saying that he wants me to debunk this video about horizon drops. However, if anybody knows of this URL, can they tell me what it is? Because it isn't a YouTube video. It's youte.be. So it's u2.be. He's trying to make me click a link that isn't for YouTube, but it's trying to mimic YouTube, but with a dot between the U and the B. Sorry?
YouTube link.
I mean, all that's fair enough. I think, trying to debunk horizon drop. I guess my counter would be, well, then you have to debunk horizon staying the same.
Yeah, no. The reason I'm asking this is that I don't want to click the link and find out that it's some kind of hack or some kind of false website, because it doesn't seem to me that it's actually YouTube. If it was YouTube, it would just be spelled YouTube, not youtube.be. Sorry, I'm completely hijacking your point here.
No, you're fine. I was gonna say something about the what was I gonna say about the whole Wolfie thing? Yeah, I don't know. The horizon drop thing. Oh,
no, you've lost track. I'll bring you back on because that was ace. So you're talking about horizon drop, and if you're going to try and assert again the leading edge of the sphere is dropping away from you, which is what they claim with horizon drop, then you've got to explain why it's staying the same. I mean, I'd love you to labor that again, please.
Right. No, that was another point earlier, was that if you look at it, model yourself, put yourself on an earth curve calculator and picture that horizons are physical things, and you're looking across a bulge of earth curve at another object far away, and you raise yourself in height 2 feet, 3 feet, whatever it is. What happens to the line tangent to assuming you stayed you didn't move your head or anything, you just went straight up. What happens to that line? It moves straight up with you, right? it doesn't continually drop down around the curve so you see more of the object. Your horizon immediately drops in that scenario. Immediately, within 2 feet of jump up and down, it should drop, if that's what a horizon is, right? Or you have to assume that as I jump up and down, I'm now looking down. It's a non-argument. I just, that's the number. When I saw Earth curve calculator, I told Randy, I said that was it for me. I was just like, that doesn't happen. So that's when I took a phone onto a plane. I was like, well, when does it drop? It better be gradual, you know, it better be gradual all the way up. And it's not, it never occurs. So, and so here's my point with all the debunking of the horizon drops. Well, I would say you have to go like this lensing effect, which is, I think, overlooked, that the wing is coming closer to you, right? Well, how do you explain that? Well, it's lensing, and that's why the horizon drops. And you can do it with a cooking lid. And again, all this stuff should be scalable effects, and you can scale these things out with what's going on with like things around your house. Sometimes it's crazy, but the easiest simple explanations are the best ones. So you know, I thought, well, maybe it's the wing flex, and we went through all this earlier. I don't want to rehash it, but it's not. The proximal wing doesn't flex hardly at all. Not especially not by what Wolfie showed in the video, which was like, you know, several feet worth of the wing getting closer. So it's just lensing.
Did you see this, Nathan? The wings?
No, I wasn't here at the beginning.
Okay, right. Well, literally, Wolfie put a video out saying that the wings on the plane, as he flew up and higher and higher and higher, the horizon dropped. So it was obviously proving a globe. And yet, what's happened is that once we've looked into this, not myself, this is what Travis has done. Travis has looked into this, and he's realized that the wings actually flex. So the ends of the wings are actually flexing up. So it would lower the horizon due to the flexing of the wings, nothing to do with Earth curve.
Well, and that's not even that.
Totally
that's part of it.
Wolfie totally debunked him.
I'm confused now because Life is Short said the complete opposite. Just give me your explanation again.
No, he's right, but that was only part of the issue. So the proof was that the horizon dropped when compared to this airplane wingtip. That was the point of his video. But was not mentioned was that wingtips rise in flight, right? So that's issue number one. So you could stop right there, I suppose. Okay. But what I found in his video, and what I found with personal observations of doing this, is that his wing is brought closer to you, right? So mark this wing out, where this smudge is on the wing here versus where this smudge is on the wing when he's on the ground, right? And you can mark out the slats, the flaps here, like what the markers are. And as he gets higher in elevation, the wing gets closer to you, okay? So how does that make sense? What's causing that? Why does the wing get closer to you? Well, it's because it's lensing. And so as the plane ascends in height, the cabin pressure is increasing on and this is my assumption, what's going on, why it's bowing out the window, or some part of the window, either the inner pane or the middle pane, or some part of the window is bowing outward and creating a convex lens. And that's when you do this with your cooking lid, you can see that you drop the horizon and you bring everything closer in that was below the center point. That's, to me, pretty straightforward. You know, that's why this horizon is apparently dropping, A, due to wingtip flex, and B, that you're getting lensing because you see the wing getting brought forward. Does that make sense?
How do you know it's not being taken in a turn?
Well, no, well, that was his argument, right? So he's saying that this is completely level. So that's always their argument too, as for why you can't confirm, like in high altitude balloon footage, that the horizon didn't drop because you're now looking down. Well, and that's a good argument for high altitude balloons, not so much for planes, because planes seem to fly awfully level once they get up into altitude. So, and you can, and I've done several. I'll take a snapshot over like several, several minutes, right? Snap, 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 just to see if the plane was, you know, subtly moving up or down, or if it was, you know what I mean? And it doesn't, it's flying level. So anyway, does that make sense? I don't want to belabor that one too much.
Yeah, fair enough.
Yeah, maybe watch it back, Nath, because I mean, literally like an hour ago or so, he was going through this.
Yeah, fair enough.
Well, what are you seeing, Nathan, or what's the concern, I guess?
No, nothing else. Just my gut reaction would be, how do you know that the plane's not banking when the top picture's taken?
No, you don't. You don't. You just have to trust that Wolfie says that this plane was level at this point. But yeah. So then what I would say is then add a third reason as to why the horizon's not dropping. 1, wingtip flex. 2, convex lensing of the window. Number 3, that it's the pitch of the airplane or whatever, right?
Yeah, it's pretty weak, but there we go.
Yeah. All right. So this was another great one. This was from JMac, where this is the effect of if my eye is at the same level of the tip of a mountain, what would happen? I think Chris, you did a model of a ship moving off into the horizon the other day, and you were saying how you thought possibly that the ship would disappear. I think it was like top first or something to that effect if it moved off, and you were just kind of spitballing through the perspective argument. But I just wanted to kind of clarify how something would never disappear top first unless you had compressed the top part of your visual field against a roof. Okay. Mm-hmm. So if you were watching a ship move off into the horizon, that ship must have like a roof or something over the top of it for it to vanish top first.
Really?
Does that make sense?
No.
Okay.
No, it doesn't make sense. I find it very interesting though, because it is something me and my brother were talking about it, and around the time that I made that little boat diagram, and did you see the little boat diagram that I made like a couple weeks ago?
Yeah, well, that's what I'm talking about.
Right. So when we would position the observer higher up so that he was closer to the top of the ship, the angles above the observer's eye line would now be the smaller, more compressed angles, as opposed to the ones beneath his eye line being the compressed ones when he's lower down. So I was just, like you said, I was just spitballing, and my thinking was, well, they're smaller at the top when he's higher up, so wouldn't the top of the ship disappear first?
You're modeling them against a screen, right? Where you're raising your eye height along a screen, and that's, so you have to have compressed it against something, a tangible thing, in order for them to compress. So the ground is what is always closer to us than the sky when we're outside, right? You can never, unless someone knows what the height of the sky is, but if you were to somehow find that out and you were to rise in elevation to the point where you met the roof of the sky, okay? And now you were to watch something move straight away from you at that point, you're now closer to the sky than you are to the ground, and the thing would disappear top first at that point.
Okay, how about this? So right now what you have on screen, what would happen? Let's say you took away all 4 walls, right? Imagine you took
now you're just in like a white space, like a nothing.
Right, imagine you're in a white space, but you still have the mountains there. Imagine they're just kind of moving away. Would they not continue to get smaller even if you didn't have all these, surroundings?
Right. So I've thought about that. I'm not entirely sure. I think I don't know a scenario where that occurs. There's always a tangible object with which you're comparing something against, like a floor or a ceiling or a wall or whatever. So I've tried to do that thought experiment, I guess, and I'm just not sure.
Yeah. Well, I mean, I don't.
Have a bash. So if you imagine you're on an aeroplane and you're looking out the window at another aeroplane, in other words, you've got no walls or ceiling to limit the angle to the top or bottom of it, then you only have the angular resolution to take into consideration. It will, as the Globers assert when they're comparing it to something disappearing across the deck, it will disappear uniformly. In other words, it will compress in a uniform manner because there's nothing limiting the visual field, like in this example on the right hand side. So you've got the guy's eye line with the deck that he's looking over, causing the limitation to the bottom half of the field of his view. Well, if you flip that entire diagram upside down So you've literally got him hanging off the ceiling. Well, the same thing's going to happen.
Right.
It doesn't matter if instead of it being mountains, it's smoke detectors, just so you can visualize something that is actually hanging off a ceiling. So with that depiction upside down and those mountains being smoke detectors, they would disappear. I'll have to phrase it carefully, from our perspective, looking as we do, to the guy who's hanging upside down. So to our vantage point, they're disappearing from top down because of the limitation of the top field of view when compared to the ceiling. But if you've got no ceiling, then the top angle is infinite, essentially infinite. We don't know what the sky is.
I'm not entirely sure. You know, the example earlier was, if I'm in a giant white corridor with no tangible objects anywhere, and no floor, no ceiling, no nothing, what would the size of something be if it were set in front of me? Well, it would be, I guess, whatever, it would line up along these potential angular or these visual field lines. It would line up along these transversal and orthogonal lines that are potential lines at some rate. And then when it moves away from me, it would move away from me at some rate. I just don't know what that rate would be. And I've tried to kind of come to terms with that, with what would the rate be in a completely non-compressed world. And I guess it would still be half the distance, double the size, and or double the distance and half the size, and then and some kind of factor in for the angular resolution limit. But it's just a thought experiment, I guess, that I just don't know the complete answer to.